In this lesson, we're going to take a look at parallelograms and different properties of parallelograms that we may not have encountered or looked at in the past. So let's first of all define what a parallelogram is. A parallelogram is a quadrilateral. So we know it has four sides. That has two pairs of opposite parallel sides. Let's go ahead and jump to our first theorem, 8.3. It says that if a quadrilateral is a parallelogram, then its opposite sides are congruent. So this is probably a characteristic that you already knew about parallelograms. If we know it's a parallelogram, QR is not only going to be parallel to PS, but it's also going to be congruent. And same thing goes for QP and RS. Those are also going to be congruent. So in a parallelogram, opposite sides will not only be parallel, but also congruent. Just a quick reminder. So when we talk about parallel sides, remember that we're using arrows. And when we're talking about congruent sides, we're just using the lines, the slashes. Theorem 8.4. If a quadrilateral is a parallelogram, then its opposite angles are congruent. This is one that you may or may not have seen in the past. So if we know that this is a parallelogram, angle P is going to be congruent to the angle opposite, which in this case would be angle R. And angle Q and angle S, those opposite angles will also be congruent. In this first example, we're going to use those properties to find the values of X and Y. So let's first of all focus on X, which in this case is a side length. So because it is a side length, we're going to look at the side FG and the side JH. Because those are opposite sides and we know this is a parallelogram, we know those have to be congruent. So we're just going to set up our equation, setting those equal to each other since we know they're congruent. And we'll solve for X and come up with a value of 7. Finding the value of angle Y, it's actually going to be even easier than that because we can see in the parallelogram that Y and the 68 degrees, those are opposite angles. So they're going to be congruent. So without any work, we know that Y is going to have to be equal to 68 degrees. So as long as you know those characteristics, the math behind that is really, really easy. All right, our next theorem. This one says that if a quadrilateral is a parallelogram, then its consecutive angles are going to be supplementary. So with this, we're talking about consecutive angles now. We know that opposite angles are congruent. We just talked about that. So we know that these are congruent and these are congruent. But now what we're saying is that consecutive angles are going to be supplementary. So this really does kind of make sense because if we think about a quadrilateral, we know the total is 360 degrees. And if we see that we have these two pairs of congruent angles, if we add them together, we know it's going to have to equal half of that total, or in other words, 180 degrees. So opposite angles in a parallel are going to be congruent, and the consecutive angles are going to be supplementary. Let's take a look at this example of a gate. So here we have a gate that has several parallelograms in its design. We have one specifically that we're looking at, which is labeled as ABCD. Now we know it's a parallelogram, so we already have that information given to us. We want to find the measure of angle ADC when the measure of angle DAB is 65 degrees. So DAB, we know this one is 65 degrees, and we're trying to find, let's call it X, which is the measure of angle ADC. So if we see that those are consecutive angles, we know that the measure of angle ADC and the measure of angle DAB are going to have to be supplementary. So when I add those two together, I should get a total of 180 degrees. Well, measure of angle ADC is the one that we're looking for, and we're calling that X. Now we know the measure of angle DAB is 65, so we can substitute that in. And then we can just solve this for x, subtracting 65 on both sides, and coming up with an angle measure of 115 degrees. All right, moving on down to the next example. Here we want to find both the measure of x and y. So here you see x is part of a side length, y is an angle measure, and we're also going to try to find z over here. Forgot about him. Z is another angle measure as well. So let's go in alphabetical order. Let's figure out what x is first. We see that Kn and Lm are opposite sides, and since this is a parallelogram, as shown by the parallel sides here, we know that those sides have to be congruent. So 2x minus 3 is going to have to equal 37. Just go ahead and solve that equation for x. And we should get an x value of 20. If we're looking for the measure of angle y now, we see that's opposite angle L, so we know that those two angles have to be congruent. So again, without really any work, we know that the measure of angle y is going to have to be 123 degrees. And then lastly, if we look at z, now we don't know the measure of angle m, so we can't use that same theorem, that same characteristic, but we do know the measure of an angle that is consecutive or adjacent to that. So we know that these two angles here are going to have to be supplementary, add to 180 degrees. So if I take z plus 123, it's going to have to total 180. If I then just solve for z, subtracting 123 from both sides, get a value of 57 degrees for that angle z. All right, and then down here to our next theorem. So theorem 8.6 says that if a quadrilateral is a parallelogram, then its diagonals are going to bisect each other. So in a parallelogram, connecting opposite vertices is going to create a bisector. So point M here basically is going to be the midpoint of both of those diagonals, and then we'll see that QM and MS are going to be congruent to each other. And then PM and MR are going to be congruent to each other. Let's take a look at an example that includes that property. In this example, it says the diagonals of quadrilateral STUV intersect at point W. We want to find the coordinates of point W. So with this, first of all, let's make sure that it is in fact a parallelogram. We can see that TU is definitely going to be parallel to SV since those are both horizontal lines. If we take a look at ST and VU, now we don't know the exact coordinates of ST, but let's go ahead and say that that is in fact 1.5 for our x value. So if we look at our rise and our run, if we try to find the slope of that, we're going up 5 and over 1.5. If we look at VU, again, let's assume that this is an x coordinate of 0.5. We're going up 5 and over 1.5. So without calculating the actual slopes of these, we can see that the rise and run are the same. So we know that ST and UV are going to have to be parallel as well. Now, let me go ahead and get rid of some of this extra information. Let's clean this up a little bit here for you so we can see what's going on a little bit better now for our problem. So here we have those sides being parallel. We're trying to find the coordinates of point W. Now, since we know this is a parallelogram and we see our diagonals being drawn, TV and SU, we know that those are going to have to be congruent. Now, beyond that, we really don't even necessarily care what the lengths of those are, but if we know that those are congruent, we know that W is the midpoint of those segments. We can probably take a guess at what the coordinates of point W are, but in this case, we do know exactly what the coordinates for point U and point S are since those are integer coordinates. So what we're going to do is we're going to look at the coordinates for point S and point W, and we're going to find the midpoint of that segment, and that'll tell us the exact coordinates of point W. And if you remember our midpoint formula, basically we have our x1 plus our x2, so we add our x coordinates, divide by 2, and then y1 plus y2, add your y coordinates, divide by 2, and that gives you your midpoint. So point W, we're going to take our x coordinates, which for S, we have 0, 0, and U, we have 6, 5. So we're going to take our x coordinates, add them together, divide by 2. Take our y coordinates, add them together, divide by 2. And we should come up with coordinates for point W of 3, 2.5. All right, and it appears that point W is probably halfway in between 2 and 3 here. So that decimal definitely does seem to be accurate. Let's move down to the next one. Here we have a parallelogram. Tells us it's a parallelogram. We want to find the length of MH and the length of FH. So because we know it's a parallelogram, we can see that those diagonals are going to bisect each other. So FM and MH are going to be congruent to one another. So if we know that FM is 5, we know MH also has to be 5. And if we know that those two lengths are both 5, then the total of them, all we have to do is add them together. The length of FH is going to have to be 10. All right, so let's shift gears a little bit. So the next section is going to be looking at showing that a quadrilateral is a parallelogram. Now, to this point, you've probably always looked for parallel sides to be able to classify it as a parallelogram. But with the properties that we just talked about, the theorems we've just talked about, there are some other ways we can show that it's a parallelogram as well. You can see the first one is to show that both pairs of opposite sides are parallel, which is our definition, which is probably the way that you're used to seeing. We can also show that both pairs of opposite sides are congruent, so that's enough to show that it's a parallelogram. If we show both pairs of opposite angles are congruent, that's enough to prove it's a parallelogram. Fourth one, if we show that one pair of sides is not only parallel but also congruent, so the same pair of sides, parallel and congruent, that's enough information to show that it's a parallelogram. Or if we were to show that the diagonals bisect each other, that's enough information. So 5 different ways that we're able to determine if a quadrilateral is in fact a parallelogram. Let's take a look at some examples. So here's the first one. We want to find the value of x to where quadrilateral PQRS is a parallelogram. So when we look at our diagram, we see expressions here representing the length of PT and TR. If we look at segment QS, we can see that basically T is our midpoint. It's bisected, so QT is congruent to TS. So we're going to kind of use that last piece to where we want the diagonals to bisect each other. So in this case, if they were to bisect each other, 5x, which is the length of PT, would have to equal 2x plus 9, which is the length of TR. And then if we solve that for x, we come up with an x value of 3. So basically what we're saying is the only time that this quadrilateral will be a parallelogram is if x is 3. If x was anything else, this shape would actually not be a parallelogram. So it has to be 3 in order for it to be a parallelogram. Next example is taking a look at a rough diagram of some headlights of a car. So we see that they have this shape here shown. We want to explain how we know that angle B is congruent to angle D. So we can't just say that opposite angles are congruent because, first of all, we don't know that it's a parallelogram. So we first of all need to determine that. If we look, we have a pair of sides. So we see that BC is congruent to AD. We also see, based on the notation, that BC is parallel to AD. So because that pair of sides is not only parallel but also congruent, we know that ABCD has to be a parallelogram. Now that we have basically proven that it's a parallelogram, now we can go ahead and say that angle B and angle D are congruent because they are opposite angles in a parallelogram. All right, let's look at another example. Here we have a basketball hoop. So this is an adjustable basketball hoop where AB and DC are adjustable supports of the hoop. So AB and DC, these are adjustable supports that can shift. So basically this hoop can go up or down. These are going to be fixed lengths, obviously. So that will adjust and create different angle measures here. We want to explain why AD, so why the backboard, will always be parallel to BC, which basically represents that pole. So when we look at this, we're seeing lengths, which is probably going to be valuable to us. If you look, you may notice that DC and AB both have measures of 36 inches. And then AD and BC both have measures of 18 inches. So we see that AB is congruent to DC, and AD is congruent to BC. So because we have opposite sides congruent, we know that ABCD is a parallelogram. So now that we know it's a parallelogram, well, one of the main characteristics of a parallelogram is that the opposite sides have to be parallel. So because ABCD is a parallelogram, AD must be parallel to BC because they are opposite sides of a parallelogram. And when you're explaining these or justifying them, you don't need to really cite any theorem numbers or names or anything like that. We just want to make sure that our descriptions are clear and accurate, and we want to make sure that we're always getting this first part proven, which is that it is a parallelogram. Because we have to prove that it's a parallelogram before we can then talk about characteristics of a parallelogram. All right, let's take a look at this last example here. So we want to show that quadrilateral KLMN is a parallelogram. You can see we have a quadrilateral, which is on the coordinate plane, and we see coordinates for each of those points, each of those vertices. So we have a couple options as far as how we could determine if this was a parallelogram or prove that it is. We can look at the slopes of the different sides, and we could also look at that in combination with the lengths of the sides. We could just look at the lengths of all the sides. We could look at the midpoint and try to show that that is the midpoint of both diagonals, so they would bisect each other. I think probably the easiest way to prove that it's a parallelogram or in a coordinate grid is simply to use slopes and show that the opposite sides are parallel. So if I look at the slope of K to N, I see a rise of -4 and a run of 2. So slope of Kn is going to be -2. If I look at the opposite side then, Lm, I see a rise of -4, a run of 2. So we can see that the slope of Lm is also going to be -4 over 2, which is -2. All right, so we can see based on the slopes there that those two sides are parallel. And then if I look at the other pair, so KL, looks like we have a rise and run of 2, which is going to give us a slope of 1. And then the slope of NM looks like we're going up 2 over 2, which again is the slope of 1. So once we identify all of those slopes, we see that, and let's just kind of summarize this. So we see that Kn is parallel to Lm, as shown by the congruent slopes there. And we also know that KL is going to be parallel to NM. So because those opposite sides are parallel, we know that KLMN is in fact a parallelogram. All right, that's it for our notes today, and taking a little deeper look at some characteristics of parallelograms. Hope you enjoyed. Please, as always, let me know if you have any questions.